In this video, what we are going to do is look at the origin of the chemical shift in NMR spectra. We are going to focus this discussion mostly on proton NMR spectra, such as the representative proton NMR spectrum sketch I've shown here, as well as carbon NMR spectra as well. By the end of this video, you should understand what the origin of the chemical shift is in an NMR spectrum, and you should also be able to deduce why certain functional groups have chemical shifts that are much further to the left end of this spectrum versus the right hand end, to justify why some functional groups have very different chemical shifts than others. So let's go ahead and get started with that. Now, as we think about this concept of chemical shift, that is, where along the x-axis are we going to see signals for different protons from within a molecule, we need to go back and think about some of the fundamentals of NMR to consider how different protons have different chemical shifts. In other words, why do we see protons at different positions along the x-axis rather than all protons showing up at a single position along that x-axis? Because if we think back to what we saw a couple of videos ago, where we looked at the origin of this magnetic resonance phenomenon, what we saw then was that if we consider that we can think of protons, nuclei, as behaving like child's toys, the top that spins, if they are in no magnetic field, the top essentially spins randomly. So we have schematically here these circles with arrows going in different directions, indicating that the top is not within a magnetic field, or the nucleus is not within a magnetic field, and it's just kind of randomly hanging out there with any number of different spins going on here. On the other hand, once that is placed into a magnetic field, what we saw was that the spins orient so that there are two spin states here, one of lower energy, which I'm representing down here with the red laser pointer, and showing that spin of the top, or spin of the nucleus, oriented upward, whereas the one up here at the higher energy is oriented, that spin going oriented downward with the schematic arrow. And there's that energy difference between those two, so that when the nucleus is subjected to the exact right magnetic field here and electromagnetic radiation, what happens is that this spin flips from positive to negative, and we call that resonance. And we can detect that delta E value, the resonance energy, the energy required to make that spin state switch from one to the other. And that requires the right magnetic field and the right amount of electromagnetic radiation to create that resonance frequency. And that resonance energy is what is detected, and ultimately what we are going to plot as the chemical shift on the x-axis of our proton NMR spectrum. However, based on the chart that I have given you here, the schematic, we would, based on this information, say, well, it looks like all of the protons in a molecule would absorb the same amount of energy, have the same resonance energy, so that they would all be detected as a single signal on the x-axis. That is not the case, because fortunately for us, based on the different environments within a molecule that a particular hydrogen is in, we see a variety of different chemical shifts. So we can ask the question of, why do we see different chemical shifts? The other way that we could look at this, other than saying why do different chemical shifts exist, is we could also frame the question as, why do different protons have different resonance energies? Because it is the resonance energies that is going to correspond to where the chemical shift resides along the x-axis. So the basis for why different chemical shifts exist, or in other words, why different hydrogen atoms in a molecule have different resonance energy, just different energies at which, when they're placed into a magnetic field, they undergo this transition. The reason is going to be because of the fact that electrons within the molecule are going to create magnetic shielding. So what we mean when we say that electrons are going to create magnetic shielding is that regions of high electron density, where the proton is surrounded by a high electron density, are going to be shielded from the magnetic field. They are not going to feel the magnetic field's effects as strongly as protons that are in regions of the molecule where there is less electron density, less shielding. So this business about electrons creating magnetic shielding, what we're referring to is that hydrogens in regions of high electron density are going to feel a magnetic field, experience a magnetic field that is weaker than the actual applied magnetic field because they're being shielded by the nearby electrons. So protons in regions of high electron density experience a weaker magnetic field than what the external field is. And the reason they're experiencing that reduced, weakened magnetic field is because they are shielded by electrons. So, in other words, regions of high electron density within a molecule are going to be shielded. They are not going to experience the magnetic field as strongly, and as a result, that is going to cause them to have an observed delta E value here in that magnetic field that differs from protons that are deshielded, meaning protons that are not in regions of high electron density. And so we end up with a spectrum of different delta E values here that will correspond to the strength of the magnetic field that a particular proton is experiencing, where a proton that is in a region of high electron density is going to be shielded from this magnetic field effect, whereas a proton that is in a region of low electron density is going to be very deshielded. It is not going to have a blanket of electron density around it to alter this delta E value. And so as a result, we end up with a full spectrum of different chemical shift values. So what we can do is we can look at that information and apply it toward a table or chart of representative chemical shift values. And we can look at the impacts of this shielding effect on the exact chemical shift of different types of functional groups. So what this chart shows, which by the way is available in your packet of information that goes along with NMR, it is showing us representative proton NMR chemical shifts. In other words, based on empirical data, based on experiments being done over a period of many years, what approximate range do we expect to see protons in different chemical environments show up in, where we define the chemical environment as how shielded or deshielded a particular proton is from a magnetic field. We describe the left-hand side of this spectrum, going further to the left here, as being the so-called downfield end of the spectrum. And we could also describe downfield as being equivalent to those protons that are so-called deshielded. So downfield means a lower magnetic field is required. A lower magnetic field is required in these cases because of the fact that these protons are in a deshielded environment, an environment that is electron poor. In other words, the protons that are present in this deshielded downfield environment are feeling the full brunt of force of the magnetic field. They have no blanket of electrons to shield them from that force. And so therefore, they are downfield. They require a very low small magnetic field in order to elicit the change from one spin state to the other, because they don't have that blanket of electrons around them to protect them or shield them from the magnetic field. So downfield will always correspond to deshielded, and it will always correspond to an electron poor environment that those particular protons are present in. This is going to show up toward the left-hand end of your spectrum here, where the left-hand end is our higher ppm values showing up along this x-axis. In contrast, if we go further to the right-hand end of the spectrum, we would describe this end of the spectrum as being the upfield end of the spectrum. When we're using the terms upfield versus downfield, we're usually using those terms relatively speaking. So we would say, for example, that an aldehyde signal here that I'm circling in the upper left is downfield relative to an alkane signal, which we're seeing here on the right-hand side of the screen. Or we could alternatively say that an alkane signal is upfield from a aldehyde signal. So upfield, in contrast to downfield, is going to correspond to protons that are very well shielded. They have a thick blanket of electrons around them, is how you could think of this. They're in a very electron-rich environment. And when we think about whether an environment that a proton is in is an electron-rich or electron-poor environment, when we think of an electron-poor environment, what we are generally thinking of is that there are electron withdrawing groups nearby. Remember that electron withdrawing groups can be electron withdrawing by induction, or they can be electron withdrawing by resonance. And these electron withdrawing groups are going to, as a result, often be electronegative atoms, or they're going to be groups that we can show electron density moving away from a particular atom by resonance. So, for example, in the case of a carboxylic acid group, the carboxylic acid group shows up right here, RCO2H in that lower left corner there, showing up all the way downfield even from 10 ppm typically. 10 ppm is often the cutoff for a variety of proton NMR experiments because not many functional groups show up further downfield from there, but a carboxylic acid group is an example of that type of group. And in particular, in the carboxylic acid group, what's going to show up downfield from 10 is our proton, shown in red here in the chart, that is bonded to this oxygen atom. And the reason why this proton is so far downfield is that it is directly connected to the rather electronegative oxygen. It's just 3 bonds away from this carbonyl oxygen, which would be electron withdrawing by induction because it is an electronegative atom. And then the other thing that we can think about is that by resonance, there is a second resonance structure for this molecule where the negative charge would go onto the oxygen, positive charge onto the carbon, OH, and that would illustrate how the region surrounding this hydrogen is especially electron deficient, because we can show that we would be taking the pi bond from the carbonyl group up onto the oxygen, moving electrons away from this region of the molecule where the proton that we are evaluating is. And so by both resonance as well as induction, the presence of electronegative atoms, we can illustrate that there's multiple ways that there are electron withdrawing effects going on here. And as a consequence of that, this is very, very deshielded. It's in a very electron poor environment. In contrast, if we go to the other end of the spectrum, if we go over here to alkanes, we have RH showing up there. And in all cases throughout this plot, the proton that is being measured, the proton for which the chemical shift is what we are looking at in the chart at a particular region, is shown in red here. So if we're looking all the way toward the right end of the spectrum, we have alkanes, such as One example of that could be something like ethane. And in this case, the proton is very well shielded. And the reason this is very shielded is because alkyl groups are electron donating by induction. So unlike at the other end of the spectrum where we have oxygen atoms that are electron withdrawing by induction, also resonance effects that are pulling electron density away from the hydrogen, instead, at this other end of the spectrum, we have our protons here that have a nearby electron donating alkyl group that is going to act to shield that proton, because the alkyl group here is going to be pushing electron density toward those protons, and that extra electron density is going to protect or shield the hydrogen atoms there from the magnetic field, creating a very electron-rich environment, creating a proton that is shielded, and hence the energy that that type of proton is going to require in order to undergo nuclear magnetic resonance is going to be very different than the amount of energy required for a carboxylic acid group proton. And then in the middle here between, we have a variety of other functional groups. In interpreting this chart and applying it toward determining the structures of organic molecules, keep in mind that the proton that is being referenced in each chemical shift region is the proton that is shown in red throughout. So in many of these cases, you will see multiple protons within the structure. For example, in the alcohol here that I'm circling, kind of in the middle of the page toward 4 ppms or so, if we follow that down, you will see HOCH, the particular hydrogen atom that we are measuring as having a chemical shift in that region is the one that is in red here. So don't be tricked or mistaken into thinking that you would expect this particular hydrogen that I'm putting the laser pointer under in the alcohol to be the one that's showing up in that 3 to 4 region with the blue bar. Instead, it is just this one that's shown in red here. The OH group has its own chemical shift because that is going to be a more generally downfielded, deshielded hydrogen atom there because it's directly bonded to an oxygen atom. So when interpreting this, the things to keep in mind are the red signals are the ones being referenced in each individual case here. And the blue bars give you a general idea about the range over which you would expect that particular functional group to show up within the proton NMR spectrum. So for example, the aldehyde group here toward the upper left-hand corner, looking at that blue bar, we can follow each end of the blue bar down and conclude that we would expect an aldehyde group to show up somewhere between about 9.5 and 10. Keep in mind there can be some further variation in these groups because in each of these cases of these representative chemical shifts, we're assuming that this is the only functional group within the molecule. In reality, when we're looking at complex molecules, there will typically be multiple functional groups, and so those can have effects ultimately on the location of the chemical shift. For example, in the case of our halogen groups here, we see that, as expected, our fluorine atom that's directly bonded to our CH is further downfield than a chlorine or iodine bonded to a CH because fluorine is more electronegative, so it's more strongly electron withdrawing. But if we had a case where we had both a fluorine atom and a chlorine atom both bonded to the same carbon, that could push the chemical shift even further down field because it would create a region that was even more electron poor. So these effects of multiple groups can combine together to give further downfield effects. So in the case of a structure like this, where we have not only a fluorine but also a chlorine, we would expect the chemical shift of this hydrogen that I'm circling with my laser pointer to be somewhere here downfield. I can't tell you exactly where without doing a measurement, but I'm guessing somewhere in this region of the blue bar that I have plugged in here, we would expect that signal to show up because of the fact that there is not just one, but 2 electron withdrawing groups directly bonded there. So it's going to deshield the hydrogen atom that we're measuring here, that is the hydrogen atom that I'm highlighting in pink here, would be further downfield, further deshielded because of the fact that the fluorine and the chlorine both work together to pull electron density away from the carbon. So the more electron withdrawing groups you have, the further downfield the chemical shift is expected to be. So keep in mind that's one of your key points in interpreting NMR data is the chemical shift. It's going to tell us about the chemical environment of a particular hydrogen, where the chemical environment refers to how shielded or deshielded is that particular proton. What is the chemical environment that that proton is in? And that can give us ideas about what functional group that particular proton we're looking at is a part of. So that's a key piece of information we get from the chemical shift. The other piece of information is when we look at a particular NMR spectrum and we count the number of signals, the number of different chemical shifts, that tells us how many different types of protons are present in the molecule. So to recap, I'm going to write a couple of those things down. So our two main uses of chemical shift are the number of signals, that is the number of locations along the x-axis where we see chemical shifts, is going to indicate how many different types of protons are present. So number of signals indicates the number of types of protons that are present. And rather than saying just the number of protons that are present, I say the number of types of protons present, because two protons or more protons that are in a totally symmetrical equivalent environment will show up as a single signal. Because in order for two protons to show up as a different signal, they have to be in a different chemical environment, meaning they have to have different electron donating or electron withdrawing groups nearby. And so if you have two protons that are completely symmetrical within the molecule in terms of their location, they can show up as a single signal. So it's going to show us the number of types of protons that are present. Another feature of the chemical shift is that in addition to showing the number of types of protons that are present, it is going to be useful in deducing the types of functional groups that protons are associated with. Because of the fact that we can observe that some protons are downfield or deshielded relative to others being more upfield or shielded. So that's another piece of information that we can glean from this. So in the next videos, what we're going to look at is multiplicity integrals, and also we are going to tie that information together to build complete chemical structures of molecules by merging this with 2D NMR data as well.